I'm Paul Hegedus. I got my PhD this past spring with Bruce Maxwell and Stephanie Ewing at MSU, and I'm the co-field trial supervisor on the DIFM project. And so for this half hour, I'm going to be talking about data analysis with on-farm precision experimentation. So I'm sure by now you guys are very familiar with digital ag, since that's the reason that we're all together today. But just to sort of reiterate some points with this, the amount of data that we've been gathering or can gather off of farms has been increasing exponentially. So over time, the amount of data that we can gather from combines, from sprayers, from spreaders, other GPS tools, and then as well as satellites is just creating millions of data points that people can harness and use to make decisions. And this is really important because at the same time that we're getting more data, we're seeing sort of changes in farm demographics. And specifically, the farm sizes have been decreasing, or have been increasing, sorry, while the number of farms has been decreasing. And this is important in regards to digital agriculture because with farmers having to manage larger farm sizes, they sort of lose the ability to have an intimate connection with their land because they have so much of that land that without extra time to manage that land. And so this is where digital agriculture comes in, where we can use data to sort of augment farmers' decision makings by supporting it with decision support systems. So again, this is probably going to be a little bit of review, but this is essentially the OFPE framework that Montana State University set up. So you might have seen something similar or maybe something a little different, but it all sort of follows the same 5 general steps. So the first thing is designing experiments, whether it's for nitrogen fertilizer, could be for other types of fertilizer like phosphorus, et cetera, but also seeding rates. And then going out and applying those experiments and then collecting data on our response variables, which would be mainly grain yield. But we also here in Montana are collecting response data for grain protein content. And then once we have our on-farm data collected, which includes what the farmer applied, so they're as applied prescriptions, we combine that with satellite data that we can gather from open sources online and put it all together into data sets that we can use to analyze and model this data to come up with what are profit maximizing, or what we like to call ecologically optimized prescriptions to give farmers a better sense of what would be the best route for management in the future, given specific conditions, to either maximize their profit or maybe maximize their profit and also minimize things like nitrogen pollution. So I'm going to be talking about this step, the analysis and modeling. So when we get the data, what do we do with it? And how do we essentially get from gathering the data to coming up with a decision support tool? So this is really a data science problem. Once we get the data, we get sort of these shotgun blasts of data across our experimental variable. So in this case, we're looking at as applied nitrogen. And then in this bottom figure, we've got yield in one field, and then we've got yield in another field. So as you can see, there's a lot of noise in the data, and it also varies field to field. And that's because agroecosystems are complex. So we need to use sort of domain, and this is business knowledge, but also ecological knowledge, along with math and statistics, and then some computer science to come up with our best sort of recommendations for farmers in terms of profit maximizing nitrogen fertilizer rates in this case. And so for a long time, there's sort of been this knowledge gap of how do we characterize these sort of clouds of data that we gather from our experiments. And there's a lot of uncertainty in the literature of what is the best sort of statistical form to characterize that cloud of data. And so few examples are linear plateau models, exponential models, and quadratic models. But a lot of these sort of tools and recommendations for how to analyze this data or develop from small plot or greenhouse studies. And a lot of them are aimed for general use. So even if they do use data from actual fields, they compile data from a bunch of different fields and come up with sort of a generalized model that they think will work best across all those fields. And so people have been looking for this silver bullet, which we've found is really not the case. There's no sort of one good way to do this for all fields out there and all years that a farmer is going to be out there growing crops. And so this brings us to sort of one of the main principles of the OFD framework, is that these response functions should be built specifically for a field, and the prediction equations that we use need to be updated each year as we get new data. So things are not only field specific, but they're also year specific. And so we need to reflect that in our data analysis and when we're creating decision support tools, because what works for one farmer might not work for another farmer, even if they're just down the street. And we're also saying that what works for one field within a farm doesn't work for the field right next door that's sharing a fence. And so it's really field specific, and our analysis methods need to reflect that. So what do we do? How do we analyze this data? Well, can distill it down simply. We use statistics and machine learning techniques. But then the question really becomes, how do we know what is correct? Like I showed in a couple slides before, we can use linear plateau models or quadratics or exponential models. We can use more sophisticated machine learning, black boxes. But how do we know what is the best for a given field? And so I addressed this in a paper I wrote with Bruce Maxwell and Taro Mieno at the University of Nebraska, who's also affiliated with the DIFM project, where we essentially asked the question of how variable is the most appropriate model across fields for characterizing crop responses to variable nitrogen fertilizer rates. And so again, the question was, how variable are these methods for characterizing crop responses across space as well as time? And then how does that relate to predictions of net return? And so we had three objectives here where we're trying to forecast yield, protein, and net returns using some of our experimental fields. And just to assess, the accuracy of our crop models and how the most accurate model changes between fields, and how does it change for a given field across time. And so I'm only going to show yield results in this paper or in this presentation. And then I'm also only going to address these first two objectives. But if you want to know more, you can reach out to me and I'll send you that paper. So in Montana, we've been doing OFDE since 2015, really. And so we have some good fields where we've been doing repeat experimentation. And so for this study, we used 7 of our fields. And so they're distributed sort of across the state. These polygons here show the area that the fields fall within. And so we've got some sort of more in central Montana, in the south, some in the north. And so we tried to get across soil types as well as sort of weather conditions. And we had 7 fields total, 3 from one farmer, 3 from another farmer, and then 1 from a third farmer. And for each of these fields, we've done experimentation in 3 years. And so because all of these fields are typically wheat fallow rotations, they're cropped in winter wheat, every other year. So it's either 2016, 2018, and 2020, or 2017, 2019, or 2021. So again, this should be sort of a review for you, but what we did is we set out our on-farm experiments. So we gave farmers our trial designs and they went out and they implemented them. And then we gather the data from their sprayers or their spreaders and get that back so we see what they actually did, so that we can tie that to the yield and the protein responses that we gather from their combines. And so these are just a couple examples of some of the experiments we sent out and the resulting maps that we get after they apply the experiments for us. So you can see our different rate blocks across each of these fields and the range of nitrogen fertilizer rates that we applied. And so I'll note in this field, you see that we only went down to 49 pounds per acre. And we did that in 2021 for this field because the farmer was getting a little sick of our 0 rates. And because we had 2 prior years where we had 0 rates, we figured we could increase our sort of minimum there without too much of a penalty. But when we're setting up new experiments, we always want to include these 0 rates to make sure we know what happens if we don't apply any fertilizer, because that's important to know. And so, of course, we also have tons of satellites orbiting the Earth at any given time. And so we can use data that these satellites are collecting to sort of augment our data sets. So in addition to gathering the yield and protein data from combines and our protein monitors that are mounted in the combines, as well as our as applied data, We're also gathering satellite data. So we're gathering things like vegetation indices from Landsat and Sentinel sources, topographic variables so that we know something about the land across the field. So like things like elevation, slope, aspect, and topographic position index, which is essentially just telling us, where are sort of divots, where there are mounds across the field on sort of a fine scale, as well as things like climate. So we're gathering precipitation data and then also growing degree data for each of our fields. And then we combine that with soil data that we're gathering from satellites. So one of the key components of our OFPE framework is that when we're creating decision support systems for farmers, we don't want to be requiring them to spend extra money or hire somebody to get this additional data. So we've been playing around with these satellite-based soil measures where we can get things like soil moisture, the texture, bulk density, sand, clay, water contents, pH, and a couple other variables. So once we have all that data, so our satellite data, this is just a subset here, plus our yield, our protein, and our nitrogen data, we have to put it all together. So for every yield point in this case, essentially we overlay all those satellite layers. And then for every point in the field, we gather what the value of the overlapping satellite data was so that we get a nice data set that we can use to create our models and analyze this data. And so, like I said, we went about, testing how variable the appropriate model form was. And so we tested 5 different statistical and machine learning models. And so the first one we used was nonlinear regression model. So this would be sort of more similar to those exponential and quadratic forms that I showed in previous slides. We used a model from a paper that was for growth curves, but because nitrogen contributes to crop growth and production equals growth, we figured we could co-opt it for our purposes. So that was sort of our relatively baseline regression model. And then we tried a generalized additive model because they're flexible. They've been used a little bit by this group for characterizing these yield and protein responses. And then we tried 2 different Bayesian statistical methods. So the first one was just a simple multiple linear regression model where we used Bayesian essentially priors. So just assuming that we have some information beforehand about how these covariates influence yield. And then the second Bayesian method was a nonlinear model developed by Bruce Maxwell's previous PhD student, Patrick Lawrence. And he used this model to estimate that we need about 6 to 8 years for converging these parameters to make accurate predictions in Montana systems. So we're still a little short of it, but the model is still useful, and it was one that we tested. And then finally, we used by far the most common machine learning approach in agriculture, random forest regression, to sort of compare to these other more statistical approaches. And so the way that we went about comparing the different models is we used a sort of modified version of hold one out cross validation, but in this case we did hold 1 year out cross validation because we had 3 years for each field. And so as you can see, we had sort of 3 different split cases here where we would take 2 years to use to train our model and then 1 year to test it. So we would either gather 2016 and 2018, use it to train a model and test it on 2020, or we would take 2016 and 2020 to train our model and test it on 2018, or 2018 and 2020, test it on 2016. And then, of course, if it's the sort of shifted rotation of 2017, 2019, and 2021, we did the same things. And so our metric of performance was the root mean square error. And we chose this because the units for that are the same as our response variables. So when you see RMSE values for yield, it's going to be in kilograms per hectare, and in protein, it's going to be in percent, essentially. So percent grain protein. And so looking at our first objective, which was how do these models change across space? So how variable is the most appropriate model across our different fields? What we did is we fit models for each of those split cases, and then we averaged the RMSE across them for each field. So we have our 5 models across the top here, and then we have our 7 fields down the side here, sort of on the y-axis. And just note that these RMSEs are in kilograms per hectare. So about 1,000 kilograms per hectare is equal to 15 bushels per acre. And what we saw is that the random forest model performed the best in 6 out of 7 fields. And so this is indicated by this darker shading. It's got the lowest RMSE, so that's indicating that there's the least amount of error associated with these predictions from the random forest compared to the other models. But we see that in one field, the Bayesian nonlinear regression, so the one developed by Patrick Lawrence, had a lower RMSE than the other 4 models. So while most of the fields were best characterized with this random forest model, one of the fields actually would require using a different type of model to make decisions for that most accurately. And then looking at sort of the second best model across these, indicated by the lighter shading, we see that Bayesian approaches typically tend to do second best compared to the random forest. And then we see that the generalized additive models were not very predictive for yield. And then our nonlinear regression did well for one farmer in 2 of his fields, but still, again, the random forest tended to do the best across all of our fields. And so then our second objective was to look, how does the best model change over time? So is the best model to use for a field, is that going to be consistent? So maybe if you have 2016 and 2018 data and you're predicting 2021 model might do best, but then if you have a dry year, maybe that model won't be, very predictive for making accurate forecasts of crop responses. So we want to know, how variable across time is the most appropriate model form. So what we did here is we split them out. We split our results by the split case. So you can see, sort of refreshing, the different split cases that we have, so the years used. And then these RMSD values are averaged across all fields. And so what we saw is that for pretty much all of the models, it was best to use a wet year and a dry year to predict your third year. And so I just put here the mean precipitation for all the years. And this is just sort of generally across Montana. So it'll vary, slightly between different locations, but sort of on average what the best what the precipitation was in Montana. And so we see that, in 2016 and 2017, we got 286 millimeters. In 2018 and 2019, it was more wet, almost 500 millimeters. And then in 2020 and 2021, it was 274 millimeters. So when we're using either 2016 and 2018 or 2018 and 2020, so split case C and split case A, those are our most representative cases where we're always using this sort of middle year that was wet, and then we're using a drier year to predict the other one, essentially. And so the main conclusion from this is that representation matters. So when you're using both of the dry years, so 2016 or 2017 and 2020 and 2021, when you're using the 286 and the 274 millimeters precipitation years to predict a wet year, you don't perform as well as if you had a wet year in your training set or a dry year in your training set and you're trying to predict something similar. There was one exception with our nonlinear regression in 2018. Apparently, we were able to predict this sort of wet year well by using 2016 and 2020 data. And that is likely because there's sort of a less of a range between the 2016, 2018, and 2020 precipitation, but it is sort of an outlier in terms of, the general results across the rest of these. And so sort of some takeaways from this. Random forest does tend to do the best in making accurate forecasts of crop production and quality. And like I said, we did this with protein. I didn't share those here, but the trends were very similar for both of those objectives. So random forest tended to do the best in terms of, across space, it's very consistent. So across all of our fields, again, 6 out of 7 fields, it was best to use random forest regression for yield. And then having a wet and a dry year to forecast into another dry year typically performs the best, except for that one case where we saw the 2 dry years did well predicting the wet year. But essentially this boils down to it's good to have representation. And so that's why it's so important to have multiple years of experimentation when you're trying to develop these models so that no matter what happens in an upcoming year, you can sort of hedge your bets that you've seen it before and make a good, accurate prediction of what will come. But it really boils down to a very sort of ecological answer that it depends. So even though the random forest regression did best in 6 out of 7 of our fields, when we look at the best model for protein, it was still typically the random forest regression, but you see that in a few fields, it was different models. So either the generalized additive or our nonlinear regression that performed the best. And I will note, I should have probably put this slide on here, but in all these cases where the best model wasn't random forest regression for the protein, the second best model was the random forest regression. So even though it's not as consistent as the yield, it's still pretty consistent that random forest regression performed the best. But we're only taking a sample of 7 fields across Montana. So if we took, fields from eastern Montana, we can't definitively say random forest regression would perform the best. If we took a farm from Illinois, we also can't say that because we haven't looked at it. And that's why it goes back to, sort of the field specificity of on-farm precision experimentation, where we need to use data from a given field to make decisions for that field and to be confident in those forecasts and the recommendations that we're giving to farmers. And again, the third OFP principle reflects that: build functions specifically for a field using data from that field and repeat it year after year. Because like Patrick Lawrence found, 6 to 8 years of experimentation was really needed to make accurate predictions in our Montana systems. And I would say that 6 to 8 years is probably an underestimate, because with the way that the climate is changing and how variable we are seeing weather and climate be, we might need more than 8 years of experiments to really get a good sort of representative data set in order to make accurate forecasts and make good crop response forecasts. And so that's how we analyze the data. And so I just sort of want to touch on, what we do after that. So once we have a model for a given field, what we do is use those models to run some simulations and essentially predict what yield, and in our case, grain protein, would be for every point in the field. So that's where you get the scatter on these plots, and then across a range of nitrogen rates. So we simulated every point in the field if we applied 0 to 150 pounds of nitrogen per acre. And then we can draw curves through that and use our predicted yield and protein to calculate net return. And so once we have our net return, which is the yield times the price received for your crop minus the cost of the applications, the cost of your nitrogen in this case, or whatever you're applying, so the A there, times how much you applied, minus fixed costs. So like electricity, lube, lighting, things like labor, etc. That's how we're getting our net return. And then we also incorporate our protein schedule, so that's which bumps up our P here, so the price received based off of the protein. But essentially, we calculate the net return for each of those points. Every point across the field, we use a 10-meter grid, and then for every nitrogen rate. And then what we can do with that is go through for every location in the field and find where did we get the highest net return. And once we find that, that becomes sort of our optimum nitrogen rate. And so you can do that for every point across the field, get a site-specific optimized map based off of our analysis, or you could sort of make an average across the field and then use sort of what would be what we call the full field optimum, and use that as a single nitrogen rate that you apply, but what we've found to be the optimum and is your profit maximizing rate. So that's what we do once we have these models and after our analysis, and that's how we do it. And this is sort of our goal, finding the biggest difference between net return and the value of nitrogen loss, which I didn't get into here. But yeah, that is sort of quick primer on data analysis and methods, how we do it, why we do it, and where we go with it.